Hello everyone, welcome to my presentation. My name is Apan and today we'll be presenting our paper, Learning Adaptive Control in Dynamic Environments using Reproducing Kernel Priors with Bayesian Policy Gradients. My honorable co-authors are Dr. Raza, who recently joined Microsoft, and Dr. Lin, who is an associate professor in University of Central Florida. My presentation will start with the motivations behind our research work, then I will briefly explain the implications or limitations in classical reinforcement learning approaches for solving dynamic environments. Followed by the contributions, I will briefly introduce non-parametric reinforcement learning in reproducing kernel Hilbert spaces. After that, I will follow the methodology. I divided the methodology in three parts, like Bayesian augmented non-parametric reinforcement learning, then embedding prior and likelihood probability distributions in our cages. Then we introduced our incremental policy revised technique by similarity metric in the same arcages. Then I will explain our robotic experimental setup, and with the result analysis, I will conclude my presentation. So let's start with the motivation. Through the evaluation, humans have not only learned to remember his past actions and past decisions, but also analyze and exploit those past decisions to solve a present task in real time. Instead from this, we opted here to design for developmentally learning a systematic and effective robotic control policy in real time for our high fidelity robotic manipulators through reinforcement knowledge gained in prior interactions with the environment and analyzing those past action sampling policy distributions. Secondly, since off-the-shelf gradient methods are computationally expensive, and they always rely on a fixed parametric space, we have utilized here a vector-valued kernel embedding in a high-dimensional reproducing kernel Hilbert space instead of a fixed parametric space to address the computational hurdles in the off-the-shelf policy gradient update methods while adapting current policy to the varying system dynamics. And finally, we have exploited the blessings of a vector space properties that is already inherited in the Hilbert space for biasing the current policy search through a similarity metric to acquire the best benefits and most appropriate directions from prior probability distributions. So what are the current limitations or implications in classical reinforcement learning approaches? So first, let's start with the Monte Carlo simulation. In MC estimation, policy gradient is often estimated through finding the expected value of the reward of a Markov chain or a trajectory, which is defined here by psi. And the integral is calculated through this function where this capital M is the number of trajectory that we have collected, and this small t is the length of each trajectory, where this log pi actually shows the probability of taking action ATI at the state STI based on the current representation through theta. This unbiased estimation in Monte Carlo simulation highly depend on a assumption that the variance of the system will vanish as we collect uh, almost infinite numbers of trajectories. And this integral is only dependent on the sampling distribution and stationary Rio distributions. So whenever we face a problem with high variance and evolving Rio distributions through time, classical approaches failed miserably and they perform non-optimally. Moreover, they show parametric divergence when faced with high variance environments. Now let's discuss with what are the problems that Bayesian learning or Bayesian quadrature faces when solving a dynamic environments. So in Bayesian reinforcement learning, policies are often modeled as a Gaussian learning or a Gaussian process so that they can represent all the uncertain dynamics of the environment. But the problem here is that the mean of a posterior distribution of the gradient is computed with the expected value of R with the probability of the current trajectory and the current parametric representation theta. Here dm is a set of samples which also encompass the noisy observations. So this integral can be decomposed into two parts. One is the Gaussian prior function f psi theta and its current probability distribution pr psi of theta. So in the Bayesian quadrature, this gradient estimation is highly dependent on the assumption that prior moments can be aggregated into a normal Gaussian process-based distribution. And secondly, this parametric space theta can be used for determining the posterior direction or posterior gradient estimation. In non-stationary MDP settings, both these assumptions fail and they often degenerate the posterior estimation process into an infinite regress, which eventually fail to find a convergence sequence uh, for, uh, uh, for the posterior estimation. Now let's focus on the contributions of our work. So our proposed development and developmental reinforcement learning utilizes Bayesian exploration strategy to incrementally bias the policy exploration of non-doing learning by exploiting past policy distributions to tackle central challenge of explosion of sample complexity if the environment imposes large inherent variance. Secondly, our DRL methodology leverages kernel embeddings in an RPHS whose complexity remains linear and tractable. Unlike parametric Bayesian quadrature, which suffers severely from non-tractable learning complexity in non-stationary settings, here we assure a tractable representations of prior and likelihood probability distributions. Thirdly, kernel-based non-parametric learning framework also resolves the serious problem of high parametric divergence in dynamically evolving state transition distributions and reward functions. And finally, our judiciously prioritize the past task transitions using a dot product-based similarity matrix computed within an RPHS before storing them into a replay memory such that our DRL can optimistically trace useful transitions later when required. Now let's talk about the non-parametric reinforcement learning in RPHS. So in non-parametric methodology, the action mapping policy is often defined as a multivariate Gaussian models where the mapping functional age maps each state to its compatible actions. This mapping function ages belongs to a vector valued RKHS, and we also assure here that the reproducing property of the RKHS holds true, and this reproducing property is a vector valued reproducing property. Our learning objective is to find that functional age star which can actually maximize our utility of the reward function, and the reward function is a discounted reward here. And through formulation of the Fletcher derivative, we can actually formulate the gradient in the RKHS through this equation, and this is one of the empirical equation that makes a easy calculation of gradient. Now there are two important things that I should mention, that we don't need to do any scaling of a fixed parametric space, which often fails to do a posterior estimation for dynamic environments. And secondly, we do not need to retain a fixed parametric space. Rather, we just need to do the repositioning of the kernel in the support of current Markov chain that we are following. So from a top view, our methodology actually exploits the actor-critic algorithm, which has a Gaussian-based Bayesian quadrature and a non-parametric kernel-based embedding learning. So if we follow this figure, we have a actor net and we have a critic net. We update our kernel based on the current policy I am following and based on the current observations I am getting. And with this kernel map, we are updating our critic net and we are getting the Q values from there. So let's move into the methodology section. So let's consider we have a task domain A, which comprises of n numbers of actions, and if n tends to infinity and all these actions are explored with a old policy, that is pi h old, we can say based on central limit theorem that pi h old has totally generalized over the task domain capital. Now what happens, we have a new task O plus and our domain has a new view or a new distribution that is O plus. So our central ask or central investigation in this paper is that how much pi h old will be helpful to get a new upgraded policy pi h plus. So we can do a naive solution. We can store all the policy parameters for O, O plus plus and all the future task domains, and we can aggregate a global policy. But such kind of solution is very memory intensive and they take a huge bookkeeping. So instead of doing a huge bookkeeping of a large policy parameters, our method actually learn a kernel-based representation through the prior embedding of the pi h old, and this works through a Gaussian process. To have the likelihood function in the same age, we also learn a kernel mean embedding for the likelihood function, and the blessing here is that we don't need to rely on a fixed prior parametric space. Now let's move into the how we do the likelihood embedding. So likelihood embedding is calculated as a mean kernel embedding here, where K is a matrix valued Gaussian kernel and OY is the current observation. And this kernel embedding is represented as a conditional distribution that depends on the prior embedding. Here MMD is called the maximum mean discrepancy, and it calculates the difference between the current probability of the likelihood function and the prior likelihood function. And this discrepancy is actually measures a similarity of the probability of the current event with the prior event. Now, this mu function or this mu t prior actually encrypts the state distribution of the hindsight knowledge captured by the old policy, that is pi h old. And this mu t prior is represented in the same vector valued kernel space, that is h, through a Gaussian process. So this GP takes the mean value of the old functional and it calculates a MMD between our target policy and the old policy. Now, this MMD actually works with a similarity metric between mu t target and mu t old, and if the divergence calculated through this MMD is decaying, we can say that the hyperparameters of the old policy is useful and they can guide the target policy to adapt to the new observation and plan a new task. Now we talk about the incremental policy revise technique. So posterior estimation or inference is a probabilistic estimation to adapt or revise the prior based on the current observations. So here we links the likelihood estimations with the prior to get the kernel embedding of muted target, which essentially perturb our gradient params tau and lambda for the target and old policy. And also the inner product based evaluation between muted old and muted target perturb the confidence impact, that is psi t1. That psi t1 actually represents our confidence on the or the belief on the non-stationarity happening in the environment. And through this meter target, we also update our target mapping functionals. So we also talk about the SM gradient direction that we calculate through the inner product based similarity metric between our old and target policy gradients. So since RL is a reward maximization technique, we always need to follow a ascent direction in the solution space so that we can maximize the reward and we can reach the global maxima. So if we need to relearn a new policy with updated a priori moments and with new observations, and if our old policy gradient goes outside epsilon neighborhood of the optimal solution, then we need to relearn a new policy. And the new policy will maximize our reward only when this dot product based calculation is always greater than a positive value, that is z epsilon by 2. So there are two policy gradient inside this dot product. One is the policy gradient from our old policy, and another one is the target policy. And if this dot product always goes to a positive value, we can say that our learning is going through an ascent direction and we can maximize the reward. And we also concentrate on the convergence of our algorithm. For that, we convert the dynamic regret term into a non-negative submartingale. So dynamic regret is defined as the difference between utility at the optimal actions and the current utility. So if the lower bound that is mentioned in the previous slide is true, this RK becomes a non-negative submartingale, and if this is a non-negative submartingale, we can follow the martingale convergence theorem and we can say that RK actually converges to its optimal value. And this figure actually represents all the steps that we have already discussed. Like we have the current observations. With these observations, we update our posterior. Before that, we also update our priori based on a Gaussian process. And this pretty-net helps us to calculate the Q value function. Now let's discuss about the robotic hardware platform that we are using. We are using two robotic arms and both of them are 6 degrees of freedom. We have the TA agent, that is an independent agent with the policy pi A. We have the adaptive agent TB, which policy is pi B and it is an adaptive policy. The action vector is the 6 joint angles. The state space is defined as joint angles from both arms. The end effector poses from both arms and a binary collision flag. The reward function can be decomposed into two parts. One is a very general and generic absolute pose difference between current angle and the goal angle, and we have a negative penalty based on the collision flag. The baseline is the DDPG with a deep reinforcement learning-based continuous robotic control scheme. We have three levels of inference based on the proximity of two goal locations and their relative locations in workspace. Now let's do uh, analysis on our results. So first we will be doing a comparison on the learning curve. So if we see the learning curve, we see that our method has a significant improvement in learning convergence where the DDPG or the baseline actually fails to get a good convergence result. Secondly, DDPG shows a very high variance and cannot stabilize on the learning, but our proposed method has largely stabilized the learning, and in most cases it has performed better than the oracle that we set. We also try to address and evaluate that how much generalized our approach is based on varying goal perturbations. So we have decided to use two performance metrics. The first one is the successful trials. So this is defined as a ratio of successful trials over all the randomly sampled trials. And second is the average steps to the first success. So we can define the number of success wasted by both approaches before getting the first success. So if we see the easy mode of operation, our proposed approach gets success at 92% cases, where the baseline gets success only at 4.42%, and the baseline wastes almost 73% trials before getting the first success, where our approach gets success at 9%. Now, if we look at the hard mode of the operation, where the proximity is very close between two goal locations, the proposed approach could not get a single success and they waste all of the trials. Well, the proposed approach gets 28.16% success and it wasted 42%, but still it gets a success which is better than the proposed. Now let's look at a experimentation video that we did on the ROS based gazebo simulation platform. We see that in the left side, when both the robots are working with the baseline approach, they collide with each other. But if we see the proposed approach, the agent TB, which is this one, adopts, it stops, it revises its policy so that it can avoid that catastrophic collision which can damage the mechanical structure of the robotic arm. So we have also decided to show a simple video in our presentation on how this robot works in the hardware setup. So this video shows how this adaptive agent works when there is no dynamic obstacles present or created by this independent agent TA. So it reaches very fluidly. But when there is a dynamic obstacle present for by this TA, this robot TB works, but it stops because it feels that there is a probability of collision, so it moves back. It revisits the old policies and the prior distributions and get a good posterior distributions with observations and reach successfully the solution or the goal space. And this is a series of snapshots that we put. So here the most important part is the C and D, where we show in a transparent structure that the robot will collide if it follows the old policy. So we have reached to the conclusion part. So we can say, or we can say that the fusion of Bayesian learning and architecture embedding with DRL showcase promising performance to dynamically adapt and upgrade robotic control policy in real-world non-stationary environment. Secondly, through augmentation of Bayesian learning, we assure that our concurrent learning method gets benefited from most relevant prior experiences to handle the concurrent perturbed target task through attempting a policy update rule. So most of the real-world collaborative robotic workspaces are evolving. So integration of architectures embedding handles efficiently the problem of high dimensionality. And lastly, we plan to extend this work with more sensory data fusion and a large robotic planning with more non-static. So thanks for listening to my presentation. If you have any further questions, please contact me or my co-authors in the email addresses. Thank you, everyone.